This is the last unit of the chapter, Linear Quadratic Systems.
How many real solutions does the system y equals x squared and y equals 2x have? So to find these solutions, we can easily graph these two equations on decimals. And notice that I have I have 2 points. One is right here at the origin, and one is right here. And these 2 points are the only 2 points on both diagrams that holds on both equations that hold both statement true. Therefore, those are my solutions. And I have 2 real solutions. That's the answer. How can you use substitution to solve this system? You plug it in. It's all calculation for this one. So you plug in the y equals 3x squared plus 3x minus 5. In other words, the first equation into the second equation. Then you begin to simplify and factor them, and so that you end up having 2 solutions for x. And you're not done at this point. Once you have 2 solutions for x, you plug it back into the original equation and you come up with 2 y solutions, which is right here and right here. And finally, you put together, you say this system has 2 solutions, 2 points that holds both statements true. Okay, this is substitution. You can easily use eliminations as well, but since this one's specified that you must use substitution, so you're sort of stuck. Here you go. It says that you can use both to find the values of x and y that makes the system true. In this case, substitution yields a new quadratic equation to solve. I really like this example. This problem says Andrew kicks a ball up a hill for his dog, and the hill is modeled by a line through the origin. So here's the origin, and there goes the hill, and that's how the dog travels up. And the ball, when he kicks it, it travels according to this parabola. How far does the ball travel horizontally when the dog catches the ball? So we want this point right here, where when the ball begins to fall, when it falls to this point, that's when the dog catches it. So it's really asking for the solution of this point. How far the ball travels horizontally is the x value. How far must Laika, the dog, run up the hill? That's interesting. So I need to know this length on the hill. And I can know that if I know that this is a right triangle here, if I know the length of the 2 legs, which is x and y. And then I can use Pythagorean theorem. Okay, so that's the thought process before you begin to solve. So let's look at these solutions. I'm going to set it up. There are 2 equations here. I'm looking for that point where it satisfies both equations. So if I use substitution right here, after I simplify, I have 2 answers. One is the origin, one is the x equals 11. And if we look at this 2 functions, it makes total sense. The blue line intersects the parabola at the origin and at 11. But because we're asking for the distance, this point at the origin is not applicable, right? So we got to keep going. We're going to drop x to equals 0. We're going to keep x equals 11. If we know y equals half of x, so if the x is measuring at 11, y must be 5.5. That's the height of the ball when the dog catches it. But if I want to know how far the dog is traveling, I'm really asking for the length of the hypotenuse in this right triangle. That's why I use Pythagorean theorem, where I do 11 squared plus 5.5 squared, and then I take the square root, and that's how I come up with 12.3 feet. So the final answer is that if Leica runs approximately 12.3 feet. That's where he will catch the ball Andrew threw. Okay, so it's quite a fun scenario in this example. I really like this one quite a lot. Now we're looking at inequalities. How can you solve this system of inequalities? I listed out the steps here. Let's go one at a time. If I complete the square, use complete the square to solve the first equation, and then you're going to have the vertex form right here, right? And the parabola vertex right now, once you get this, is positive 3 and positive 8. So now it's right here. And then you can find two symmetric points on either side. Find something easier, smaller number. In this case, I chose 2 and 4. I plug it in, I have the y value, and then therefore I can sketch out. And because it's less than, it's not less or equal to, I use dotted line to indicate that this perimeter is part of the graph, but is not included in the equation. Okay? Now, second step, I shade the quadratic equation inequality. How do I do that? You can take a test point and find out if that area can satisfy this or not. And if it can satisfy this, and so you can take when x equals 3, you solve for y. Y should be 0. And then that makes this statement true. Therefore, this is the area y is less than that equation. Now, next time I'm going to graph the linear boundary line. That's relatively easier. And so you use, in this case, probably it's easier just to find the y-intercept and then find the slope and connect the dots. Well, or rather not connect the dots because it's not equal to, it's greater than. And then you have to shade the linear inequality. In this case, greater than is above, right? So again, use test points you have to. You all learned this in middle school. And now the blue part satisfies that linear inequality. And now there's this little pink part, this little slice here that has blue and it has 10 as well. So it gives that pink color. That's my solution. That's it. So it's really no different from solving linear equations and quadratic equations or inequalities separately. It's just that you put it together when you're in a system. Finally, in summary, excuse me, when we look at linear quadratic system of equations, excuse me, we can have three scenarios. In this scenario, the two functions do not touch each other. There is no intersections, and therefore there's no solutions, which really means nothing on this line and nothing on that parabola can satisfy both. In the second scenario, my straight line, blue line, actually is a tangent line of the parabola. So in this case, there's only one solution. Or it can be like the third scenario where it cuts off that parabola at 2 points, and then there are two real solutions in that case. Okay? For inequalities, as we just discussed, you solve for each one individually. You solve the quadratic inequality first, shade the necessary area that satisfies the condition. Then you do the same with the linear equation. And then wherever they intersect is the portion, the inequality that satisfies both functions. So this unit is not hard. It's just a combination of what you've learned previously, putting it together. One is linear, one is quadratic. Ultimately, you have either no solution or one solution or two solutions as your final answers. All right, guys, I will see you later. I think this ends this chapter, which is really wonderful. And we're going to move a little bit slower from this point forward because as of now, most of this information is all reviews.